Hi, welcome back to my class in Integral Calculus. For today, we will take up the third case of integration by partial fraction. In this third case, the integrand is a rational expression, but the factors of the denominator of this rational expression contains a quadratic expression as one of the factors. And this quadratic factor of the denominator of the rational expression of the integrand of the given integral is unique. That means this quadratic factor is not repeated. When this quadratic factor is repeated, that would be the last case, case 4 of integration by partial fraction. Let us have one of our examples for integration by partial fraction, case 3. Evaluate the integral of 7x plus 13 all over x cubed plus 9x with respect to x. The given integrand is this rational expression 7x plus 13 over x cubed plus 9x. And the first step is to factor out the denominator. Since the exponent of x in the numerator is less than the highest exponent of x in the denominator, we proceed with factoring out the denominator. If the highest exponent in the numerator is greater than the highest exponent of the variable x in the denominator, then we have to divide first the numerator by the denominator. But for this example, we go directly to factoring out the denominator. By inspection of the denominator x cubed plus 9x, we can see that x is a common factor. And the lowest exponent of x is 1. So we factor out x raised to 1 from each term in the denominator. The numerator 7x plus 13 is as is. To obtain the other factor, we divide each term of this binomial by the common factor x. X cubed divided by x is x squared. Plus 9x divided by x is 9. Now, this quadratic expression x squared plus 9 is no longer factorable. Therefore, we proceed to writing this rational expression as a sum of partial fraction. For the first common factor, it's a linear factor. We use a constant denoted by capital A. And we write this as approximately equal to a constant A over x the denominator of the second fraction in this sum of partial fractions will contain two constants of the form and this is case 3. One of the factors of the denominator of the given rational expression is a quadratic factor. That means the highest exponent of x is 2 in the quadratic factor. And this quadratic factor is not repeated. That means this factor x squared plus 9 is the only quadratic factor in the denominator. And for the numerator of the quadratic factor, we use two constants and we write them in this form bx plus c. If x squared plus 9 is repeated twice, that means x squared plus 9 is raised to the power 2. The next term will contain in the denominator x squared plus 9 And in the numerator, you will use again two constants. Next to c is b, dx plus e. But that would be case 4 of integration by partial fraction. Now we eliminate the denominators by multiplying both sides of this expression by the LCD x multiplied by x squared plus 9. Multiplying this rational expression by x and x squared plus 9, x will cancel out, x squared plus 9 and x squared plus 9 will cancel out, and we are left with 7x plus 13. Identically equal to a over x, we multiply by this LCD x times x squared plus 9, and x over x will cancel out, and we get a multiplied by x squared plus 9. And the second term, we multiply by x times x squared plus 9, x squared plus 9 will cancel out, and we get bx plus c multiplied by x. Now to find one of the constants, this term will be 0 when x is 0. When x is 0, this term will go 0, and this term will be equal to 0 squared plus 9 multiplied by a is 9a. At the other side, we have 7 multiplied by 0 is 0 plus 13 equals 13. And from this equation, 9a equals 13, we can solve for a by dividing both sides by 9. 9a divided by 9 is a, 13 divided by 9 is 13 over 9. So we found one of the constants. Now we take the term with containing x. If you multiply x multiplied by c, you get cx. And the coefficient of x is c. We equate that to the coefficient of x at the left-hand side, 7. Therefore, c is equal to 7. And the last constant we have to find is b. We take the coefficients of the terms with x squared. X multiplied by bx is bx squared. The coefficient of x squared is b. And here we have a multiplied by x squared is ax squared. We collect the terms with x squared, ax squared plus bx squared. And you factor out x squared, you get a plus b. A plus b is the coefficient of x squared from the right hand side. Ax squared plus bx multiplied by x is bx squared. And we factor out x squared, you get a plus b. But at the left hand side, there is no term with x squared. So we equate a plus b to 0. And from this equation, a plus b equals 0 implies b equals minus a. But a is 13 over 9. Therefore, b is equal to negative of 13 over 9. now write this integrand 7x plus 13 over x cubed plus 9 as equal to the sum of these partial fractions where a, b, c have these values. We have 7x plus 13 over x cubed plus 9x. Is equal to the sum of these partial fractions a 13 over 9 over x plus b negative 13 over 9 multiplied by x plus c 7 all over x squared plus 9. And we integrate both sides with respect to dx. With respect to x. We integrate the left hand side with respect to x. And we integrate the right hand side with respect to x. To evaluate the right hand side, we apply integration rules for the integral of a sum is equal to the sum of the integrals. And then we integrate each term separately. The integration rule for the integral of a sum equal to the sum of the integrals. This right-hand side of this equation is now equal to the integral of 13 over 9 over x with respect to x. Plus the integral of negative 13 over 9x plus 7x over x squared plus 9. And for the first term, we apply the integration rule. The integral of a constant times a function is equal to the constant times the integral of the function, which means that we can take out 13 over 9 out of the integral sign. And the first term is equal to 13 over 9 times the integral of 1 over x with respect to x. For the second term, we again apply the integration rule for the integral of a sum. We divide each term by x squared plus 9. And we get positive times negative is negative. The integral of 13 over 9x over x squared plus 9 with respect to x. And plus 7, integral of 7 over x squared plus 9 with respect to x. The first term is now integrable. The integral of dx over x is ln of x multiplied by 13 over 9. And here 13 over 9 is again a constant, so we can write it as coefficient of the integral of x over x squared plus 9 with respect to x. And 7 also is a constant in the last term, so we write this in front of the integral sign, plus 7 times the integral of dx over x squared plus 9. For the integral of x dx over x squared plus 9, we simply let u be equal to x squared plus 9 because the derivative of x squared is 2x and we have x in the numerator. Let u equals x squared plus 9, differentiate both sides, the left hand side with respect to u, derivative of u is 1 multiplied by du. Derivative of x squared is 2x, derivative of 9 is 0. Hence, derivative of x squared plus 9 is 2x multiplied by dx. And we have x dx in the numerator. So we solve for x dx from this equation by dividing both sides by 2. 2x dx divided by 2 is x dx. And the left hand side we also divide by 2. In this integral, we replace x dx with du over 2. And we replace x squared plus 9 with u. And the resulting integral is readily integrable. For the last term, we make use of trigonometric substitution. You recall from last time that if the integral contains an expression of this form, is square root of x squared plus a squared. Then we make use of this trigonometric substitution, x equals a tangent theta, where a here is the square root of 9. 9 is equal to 3 squared. Therefore, a is 3. Hence, for the last term, we let x equals 3 tangent theta. And we differentiate both sides. Derivative of x is 1 multiplied by dx. For the right hand side, we have 3 times derivative of tangent theta is secant squared theta. Derivative of 3 tangent theta is 3 times derivative of tangent theta is secant squared theta times d theta. In this integral, we replace dx with 3 secant squared theta d theta. And here we replace x with 3 tangent theta. And we simplify. In this integral, we now replace dx with du over 2. We get negative 13 over 9 times the integral of du over 2. Over x squared plus 9 is equal to u. Plus 7 times dx, integral of dx is 3 secant squared theta d theta. Over x squared is square of x. X is 3 tangent theta, square it, you get 9 tangent squared theta. plus 9. The first term is as is 13 over 9 times ln of x. And this is 1/2. 1/2 is a constant. So we multiply it by 13 over 9. We get negative 13 over 18. Times the integral of du over u. And here in the denominator, we have 9 as common factor. And 3 is a constant. Plus 7, integral of 3 secant squared theta d theta. We factor out 9 from the terms in the denominator. 9 is a common factor. Nine is a common factor. We find the other factor by dividing each term by 9. 9 tangent squared theta divided by 9 is tangent squared theta. Plus 9 divided by the common factor 9 is 1. And we simplify from one of the trigonometric Pythagorean identities, squared of tangent theta plus 1 is equal to secant squared theta. And 3 over 9, we reduce to lowest terms by dividing 3 by 3, 1, and 9 divided by 3 is 3. And the constant now is 1/3. We multiply it by 7. We get 7 over 3. The first term is as is 13 over 9 times ln of x. Minus 13 over 18. This is now readily integrable. The integral of du over u is ln of u. And we multiply 7 by 1 over 3, we get 7 over 3. Secant squared theta d theta. But tangent squared theta plus 1 is secant squared theta. So secant squared theta over secant squared theta is 1. And what is left is d theta, the integral of d theta. We have 13 over 9 ln of x. Minus 13 over 18 times ln of u. We now replace u with x squared plus 9. Because earlier we let, for integrating the second term, we let u be equal to x squared plus 9. Plus 7 over 3 times the integral of d theta is theta. Since we have integrated all the terms, we add c, the constant of integration, as the last term. But we have to solve for theta. Earlier we let x equals 3 tangent theta. So we solve for theta from that. We divide both sides of this equation by 3. We get x over 3 equals tangent theta, or tangent theta equals x over 3. Tangent theta equals x over 3, therefore theta is shift tangent or arc tangent of x over 3. Our final answer now for the integral of 7x plus 13 over x cubed plus 9x with respect to x is 13 over 9 times ln of x minus 13 over 18 times ln of x squared plus 9 plus 7 over 3 times arc tangent of x over 3 plus the constant of integration. And this completes the solution of our first example. For our next example, consider the following integral. Evaluate the integral of 3x minus 1 all over x squared times quantity x squared plus 1 with respect to x. You can see that in the given integrand, the denominator is already in factored form. One of the factors is a linear factor x, but the factor x is repeated 2 times as indicated by the exponent of x. And for that, we apply integration by partial fraction case 2, where linear factor is repeated, but the other factor is quadratic, which is unique, which means that this quadratic factor is not repeated. And to this we apply integration by partial fraction case 3. And we write this rational expression, the given integrand, as a sum of partial fraction. We start with the first linear factor x, and the numerator is a constant denoted by a. By integration by partial fraction case 2, because x is repeated, the next term repeated twice, the next term will contain x squared in the denominator and another constant we denote by b for the numerator. And for the quadratic factor, we add another fraction with denominator equal to the quadratic factor x squared plus 1. And the numerator will contain 2 constants which we write in this form. For the quadratic factor, the numerator is always of this form, a constant times x plus another constant. Now we eliminate the denominators by multiplying both sides by the LCD. Multiplying the left-hand side by the LCD, x squared multiplied by x squared plus 1 will cancel out with x squared over x squared plus 1 in the denominator of this rational expression, and we are left with 3x minus 1. A over x multiplied by x squared times x squared plus 1. X squared divided by x is x multiplied by a multiplied by x squared plus 1. The second term b over x squared multiplied by x squared times x squared plus 1. And x squared over x squared will cancel out. We get b times x squared plus 1. And for the last term, x squared plus 1 over x squared plus 1 will cancel out and you get cx plus d multiplied by x squared. You can see that one or more of these terms will be 0 if we let x equal 0. If x equals 0, then this term will be 0, and this term will be 0, but this term will be equal to 0 squared is 0 plus 1 is 1 multiplied by b, equals to the value of the left hand side when x is 0, 3 multiplied by 0 is 0 minus 1 is minus 1. Therefore, we get the first value of a constant, the constant b equals negative 1. Now, let us consider the term containing x to the power 3. We have ax multiplied by x squared is ax cubed. And here we would have x cubed if we multiply cx multiplied by x squared. We have ax cubed plus cx cubed, common factor is x cubed, and we get the constant a plus c. But at the left hand side, there is no term with x cubed, so we equate a plus c to 0. Now we consider the term containing x squared. We have bx squared, and d multiplied by x squared is x squared. We have bx squared plus dx squared. Common factor is x squared, and we get the sum of the constants b plus b multiplied by x squared. Coefficient of x squared is b plus b. But we do not have a term at the left hand side containing x squared, so we equate b plus b to 0, and b is negative 1. From this equation, we solve for d. Transpose b, positive b to the left hand side, we have minus b. But the value of b is negative 1. Multiplied by negative is positive. Therefore, d is equal to 1. Now, the term containing x, we have ax multiplied by 1 is ax. And that's the only term containing x at the right hand side. Ax multiplied by 1 is ax. The coefficient of x is a. We equate to the coefficient of x at the left hand side 3. Therefore, a is 3. And from this equation, we solve for c. Transpose a to the right hand side, we get c equals minus a. We transpose a to the right hand side, we have minus a, therefore c equals minus a, but a is equal to 3, therefore c is equal to minus 3. Now we replace a, b, c, d with their values, and we integrate both sides with respect to x. We have 3x minus 1 over x squared times x squared plus 1. We now change this to equality sign because we now know the values of the constants a, b, c, d. We write is equal to a 3 over x plus b is negative 1 over x squared plus c is minus 3 multiplied by x minus 3x plus d is 1 over x squared plus 1. And we integrate now both sides with respect to x. The left hand side we integrate with respect to x. And we obtain the given integral. The right hand side we integrate with respect to x. And we apply the integration rule for the integral of a sum, which is equal to the sum of the integrals. The integration rule for the integral of a sum, the right hand side is now equal to the integral of 3 over x with respect to x. We have positive times negative is negative, minus the integral of 1 over x squared with respect to x. And we divide 3x plus 1, we divide 3x by x squared plus 1, and we divide 1 by 3x plus 1. And the next term is positive times negative. 3x is negative minus the integral of 3x over x squared plus 1. And the last term is the integral of 1 plus the integral of 1 over x squared plus 1 with respect to x. We take out 3 out of the integral. It becomes 3 times the integral of dx over x. And to the second term, we apply the power rule. We bring x squared to the numerator. We take the opposite sign of the exponent. So the second term is minus the integral of x to the minus 2 with respect to x. Here, 3 is a constant. We take that out of the integral sign. Minus 3 integral of x dx over x squared plus 1. The first two terms are readily integrable. For this term, we let u equals x squared plus 1. letting u equals x squared plus 1, we differentiate both sides. Derivative of u with respect to u is 1 times du. Derivative of x squared plus 1 with respect to x is 2x times dx. And we have x dx in the numerator. So we solve for x dx from this equation, divide both sides by 2. 2x dx divided by 2 is x dx is equal to du divided by 2. For the last term, we make use again of trigonometric substitution by letting x equals 1. A here is 1. 1 is squared. Is equal to a squared. Therefore, a is 1. We let x equals 1 times tangent theta, or x equals tangent theta. If x equals tangent theta, we differentiate both sides. Derivative of x with respect to x is 1 times dx. Derivative of tangent theta is secant squared theta times d theta. And here we replace dx with secant squared theta d theta. We replace x squared plus 1 with we replace in x squared plus 1, we replace x with tangent theta, and we simplify. And then we apply one of the Pythagorean identities. The integral of dx over x is ln x multiplied by 3. Minus by power rule plus 1 to negative 2, negative 2 plus 1 is x to the minus 1. Divide by minus 1. Minus 3 times the integral of x dx equals du over 2. Over x squared plus 1 is u. In the last term, we replace dx with secant squared theta d theta plus the integral of secant squared theta d theta over x squared, but x is tangent theta, is square it, tangent squared theta plus 1. We simplify the second term, the first term as is 3 ln x negative and negative is positive, and we do not want negative exponent in the final answer, so we apply property of exponent. We take this down to the denominator and we get 1 over x. And here 1/2 is a constant. We take that out of the integral sign. We multiply 3 minus 3 by 1/2, negative 3/2. And we get integral of du over u, which is equal to ln u. And here, again by Pythagorean identity, the square of tangent plus 1 is equal to secant squared theta. And we have secant squared theta in the numerator divided by secant squared theta in the denominator. So the last term simplifies to plus the integral of d theta. We have 3 ln x plus 1 over x minus 3 over 2, and here our u is x squared plus 1. And the integral of d theta is theta. Since we have integrated all the terms, we now write the constant of integration as the last term. But we have to solve for theta from here. X equals tangent theta, which means that theta is equal to shift tangent or arctangent of x. Thus, the final answer for the given integral of 3x minus 1 over x squared times x squared plus 1 with respect to x is equal to 3 ln x plus 1 over x minus 3 over 2 times ln of x squared plus 1. And here we have theta, and we solve for theta from the trigonometric substitution that we use. X equals tangent theta, which implies that theta equals shift tangent or arctangent of x. And the last term is the constant of integration. And this is the solution for the given integral, and that completes our example 2. For your practice, please try the following exercise. Evaluate number 1, integral of x dx over x plus 1 times x squared plus 4. You can see that the denominator is already in factored form. One factor is a linear factor that is unique. The other factor is a quadratic factor that is also unique. Number 2, evaluate the integral of 2x minus 1 over x minus 1 squared times x squared plus 2 with respect to x. The denominator is already in factored form, but the linear factor x minus 1 is repeated twice, as indicated by the exponent 2 of x minus 1. But the quadratic factor x squared plus 2 is unique. Now, in this number 2, you will use a trigonometric substitution. Please note that the square root of 2 is equal to 2. Or to determine the value of a, we have to write 2 as a square of a number. And 2 is equal to the square of the square root of 2. And this completes our lesson for today. If you have questions about the lesson today on integration by partial fraction case 3, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Calizon, the channel of learning and leisure. Thank you for joining me in my class today in Integral Calculus.